Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you study for your final exam. So I'm going to take this whole final here, and I've written answers to most of the problems here, and I'm going to chat about how to do them. So in number one here, what you want to do, oops, come on, start by taking the 60 mile per hour and converting it to feet per second. Okay. Then draw your velocity graph, and then remember how these things, acceleration and distance, relate to it. This one right here, you're going to get by area. This one is slope. So that should get you through that problem. Moving on to number two. All right, arrow fired straight up in the air. So you should get about 510 meters and attack this by concepts of work and energy. Draw the thing at the arrow position 1. And at the highest point, position 2, write out the PE1 plus KE1 equals PE2 plus KE2. There's no work term to worry about here. You should get about 510 meters. The distance will show up in the PE2 term, the height. Okay, number 3, elevator lifted 30 meters by an electric motor. So this elevator, basically here it is, and it's moving up. It doesn't say anything about changes in speed, all right? So the changes in energy are all changes in potential energy. So if we datum the bottom, meaning we call the potential energy here 0, the potential energy here is going to be an MGH term. You should get 882,000 joules is what I got out of it. Power is the rate that energy is transferred, right? So this energy got changed. Oh, whoops. I guess we're not given a time. So if we power, the motor's sitting right here. I'm sorry. So take that horsepower. This is just a unit conversion. Use 746 watts per horsepower. How many seconds is this going to take? So power is work over time. You could also put change in energy over change in time. They're the same thing. The power here, right, is you're getting from this, and then the work, that's your change in energy, and then solve that for T. I got 118 seconds. Okay, number 4, a rock dropped off of a bridge. So when the rock is dropped, had we been given a distance, we'd be using work energy principles. But work energy principles are not time-dependent things. Here we're given a time. What we want to do is start with this. We know that that rock is going to accelerate down at about 9.8 meters per second. And acceleration is change in velocity over change in time. That's what that's equal to. That should be enough to allow you to calculate the speed. And then when it says distance, draw a velocity graph, keeping in mind it starts from rest. And then the distance is found by area under that curve. I'm not going to talk about number 5. I just probably don't think I need to. Okay, so electrical costs. We are charged by the kilowatt hour. Apparently this is a pretty old review here I've written, because right now my current bill is around 16 cents a kilowatt hour, but we're going to go ahead and use 10 for this. So 1,500 watts is 1.5 kilowatt. And if you multiply by the number of hours, now that's the number of minutes, you got to convert that to hours. You'll have a number with units a kilowatt hour. And then you can use your cost here like a conversion factor, 10 cents per kilowatt hour. I got a nickel when I ran that. These are classifications. The point of this is, can you list these in order? So I don't need you to memorize, and I'm not going to ask you to memorize numerical cutoffs for these, but I do want you to be able to take any sort of radiation like this and classify it in order of increasing frequency or increasing energy or increasing wavelength. The order is really all that matters. For example, the highest energy radiation on this list is X-rays. That means X-rays have the highest energy, the shortest wavelength, and the highest frequency. Same type of question here. All right, so this one is a parallel circuit, and a very important thing to realize about these circuits. Okay, the main equation that you're going to use in circuit problems, whether it's AC or DC circuits, this one is a DC, is voltage equals IR. That's called Ohm's law. This is kind of like the F equals MA for circuit problems. The trick is knowing what the voltage is across any given resistor. And in all my videos, you'll notice, remember, I color code these. I'm going to go ahead and use this guy right here. So the highest potential, here's the battery. Remember that the upper terminal is the positive side, means the high potential side of the battery. And in theory here, this is all wire. And remember one of my videos, IFACs, important facts about conductors. The conductor itself is an equipotential, meaning that this is all the same potential to this point. So the 18 volts is good from here to here. Well, if you look at the color, this like red to black, look over here, red to black, red to black, red to black. So the 18 volts is good across all of these. And again, that's the whole point of a parallel circuit. Voltage is the same. So if you apply this formula to these resistors, you'll get the currents here, here, and here. Now this current label I here that doesn't go through a resistor, you can't get that one from Ohm's law, but if you look at this spot right here, actually, let me redefine that. Look at this right here, like that oval I just drew. Going into that oval is the current I, and coming out is I1, I2, and I3. That's why that current I is the sum of the three, so that's where that's coming from. Now, by the way, if this were a DC, or I'm sorry, an AC circuit, about the only difference really is this will have this type of shape, okay? In an AC circuit, your voltage is probably going to be 120 volts. That is your standard RMS voltage for an AC circuit. I see no reason to give you something other than that. And then after that, the problems are basically work the same. It's about really the only difference at this level in this class, okay? So don't be surprised if maybe you see an AC circuit instead of a DC, but they are done the same way. 10 is not a problem. I don't think we talked about this a whole lot in this class, and I don't intend on putting this on your final exam. But electric fields always point away from positive charges and towards negatives. So if you pick a spot like right here, the electric field due to this positive charge is this way, the electric field due to the negative also this way, and the field is definitely to the left. I would expect that you could answer this one though. If you put a negative charge halfway between them, it will be repelled by this, attracted to this. Definitely the force will be to the right on that electron. I guess that's a question I would definitely feel okay about putting on that final. This is a transformer question. Make sure you draw, in any one of these. This is kind of like a little, I call it a schematic basically of how a transformer works and what it does, right? So you have an input voltage, Vn, and an output voltage. So the input voltage is the voltage between these 2 points, output voltage between these two. Here's a relationship for the voltage. 24 volts is what I got. Then the power on the input side is current in times voltage, and power on the output side is current out times voltage out. If we assume 100% efficiency, these would be equal. And that's how I got the 25 amps. 12, let's see, what is the velocity at 1 second? So what you have to know about number 12 is, well, how does velocity relate to a position graph? And the answer is slope. 1 second, we are here on the graph. Now this is a line. Pick any 2 points on the line you want. You're going to get the same value as slope. I used these two to get the number I got. Go ahead and repeat for B and C. Okay, here, this is a velocity graph. So this graph is telling us what this particle is doing. So for example, here on the graph, it's moving 8 meters per second to the left, assuming right positive. And I would also point out that velocity is not changing in this region here, so this object is not accelerating. So question A, when is the particle at rest? You're looking for a spot on the graph where the velocity is 0. It's probably enough about that. The questions about acceleration are about slope. That's probably enough about these. Oh, the how far. Okay, so on a velocity graph, the how fars, these are area questions. Okay, unit conversions. And you don't need to memorize any unit conversions. Any unit conversions you need will be supplied to you on the final exam. Here's, you know, the values I got. Okay, so I know that, you know, we have not had a chance to talk about this a lot, and I'll make another video or two as these examples here, but, or for example for you, I'll probably do a little more here than some of the other problems. So a hydrogen atom, you've got the nucleus, and the electrons live in these regions called shells. So in this case, we're talking about an electron that's starting in the 4th shell and dropping to the 3rd. I know I only did 3 of them, but I don't have room. I'm going to call this the 4th shell. So we have an electron here that that starts with a certain energy. And when you calculate the energy of an electron in a hydrogen atom, it's minus 13.6 eVs over n squared. So you can get a number for that energy just by putting a value here. And I'm going to double check my number here because I got a feeling that maybe I might have goofed this up. Let me just, oops. Yes, I did goof this up, by the way. This energy, 0.85 eVs is what I actually got out of that. I think I ran it for n equals 2, not 4. I'll go ahead and fix that later, but the 0.5 eVs, darn it, wish that wouldn't have happened, but this ends up being 1.36 times 10 to the minus 19th. You're going to get slightly different values here. I'm not going to do this right now, but you'll get slightly different values here and here. Oops, sorry about that. I'll try to fix the other one and redo it and repost it. But so you calculate the energy. Oh boy, to tell you the truth, I really goofed that up because I forgot the E1. Just scrap this entire thing right here. Okay, sorry about this. I will redo this and repost it. Okay. Calculate the energy at energy 4, and you do so by putting a 4 there. And don't forget it's E, that's squared. You're going to get a number. It's going to be pretty small. Calculate the energy at E1. Now when you put a number here, you get negative 13.6. Now where this formula is coming from, this isn't advanced physics here. This electron starts here with a certain energy. And when it drops to n equals 1, it gives up a photon. And that photon carries energy away with it. So whatever energy you start with has to equal the sum of these two. Just like if I start with $20 and I give 5 away. The 20, what I started with, has to equal the 5 plus what I have left, 15. That's the type of math we're applying here. Calculate energy 4 and energy 1, put those numbers in, find the energy of the photon. Once you have the photon energy, that's going to be in EVs, right? That's going to be a number in electron volts. Then you can convert it to joules by 1.6 times 10 to the minus 19th joules per electron volt. Then to get the frequency, your energy in joules is Planck's constant times the frequency, where Planck's constant is 6.63 times 10 to the minus 34th. Units are joule second. That's supposed to be a 4 there. Sorry about that. So that should get you through that problem. I'm going to have to redo number 13 number-wise. Let's see. Number 14, a photon leaves with 20 eVs of energy, or I'm sorry, a photon with 20 eVs of energy is absorbed by an electron in the ground state. How much kinetic energy is the thing going to leave with? Well, so remember what these energies are. Right, so you got your nucleus. Here's my n equals 1 state. So the energy of this in the ground state, right, is minus 13.6 eVs. And what that means is it's going to take 13.6 eVs of energy to liberate that electron and make it leave. If you add more than that, say we added 14, it would, of the 14, it would take this amount to make it leave, and there'd be 0.4 left over. And the leftover, if you will, would be a kinetic energy. Same type of deal with the 20. That's where that's coming from. So that should answer how to do 14. Okay, frequency of a photon with a 2-meter wavelength. So one of the things I want you to be able to do is go back and forth between frequency and wavelength for any radiation. So the speed of light is equal to frequency times wavelength. That's how you go back and forth between frequency and wavelength. Again, this funny little symbol is how we symbolize wavelength. The speed of light is 3 times 10 to the 8th meter per second. That's true for all electromagnetic radiation. And then we're putting in 2 meters for the wavelength, and then you're solving for the frequency. And take this 2 meters and look at the electromagnetic spectrum, and I think you should easily see that the 2 meters is not visible. Human eyes can't see a 2-meter wavelength. So anyway, there's your exam for this, or your practice test here. I hope that this helps. Do well on this thing, and we'll have a great end of the semester, all right? Hope that you enjoyed the course.